Hello, thank you for listening to this series of videos on our second module that focuses on data distribution. So we will see several topics from looking at descriptive statistics and basic statistics, looking at simple data distributions, and then more common types of distributions. So let's start with a distribution. What do we mean exactly? And often you visualize distribution with a histogram that allows you to see the spread of your data, your variable. And an example here is, let's say you're trying to see the distribution of baby weight. So you record hundreds of samples from recently born babies, you measure their weight, and you will get, so let's say you have a first sample up here that the baby has a weight of 2.1 kilogram. And so you will enter your data, you have this x-axis here of baby weight, and each bar represents a certain range. And so here might be the range from 2 to 2.5 kilogram. And so as you record this one sample, it will increase the height of the bar here by 1. So if you go and count, this could be a frequency or a proportion, but basically it's how much or how likely you are to have a sample in this category. And next sample here, weight of 3.9 kilograms. And so this bar here will increase by 1. And as you have more and more sample, you will get a shape of this distribution showing that, well, babies will typically in your samples will typically have a weight between 3 and 4 kilogram, with a distribution that goes from well, very small to very big, if you could say it like this. I'm not sure this distribution is quite accurate, but this is the gist of it. Okay, so this is an important first step, because when you have a variable, you want to understand the data you have, so visualizing it is important. And you all know some of the descriptive statistics that are commonly used in science. Our first one here is the mean. It is related to the mean, and we will be using a slightly odd sort of terminology that is related to older work in physics. So if you have an object, you can think of this object as having a position, a velocity, then it can spin. And so if you think of the term momentum, okay, the position is fixed. There's no momentum, so it's the first moment. First moment is always 0, but it's the first moment around the mean, so around the position physics. And then you'll see how our second and third moment are related to the variability, so as the moment the object moves, and so on and so forth. So I know the terminology is a little bit complicated, but you'll see that there's a second point in bringing this terminology of the first, second, third, and fourth moment around the mean, is that the equations we'll use have a certain progression showing that we are actually calculating something similar from one to the next, and that's how they're related. So the first one is the first moment around the mean. So let's focus on the mean. I'll show you the equation for the first moment, but you can think of the two as very tightly related, okay? And we have an equation here for the mean. So we'll come to the one in red here. I want you to be able to recognize this. But if you look at the one just above, you have the sum of the numbers that are in your data set and divided by the number of samples you have. and that gives you the mean. So y bar, y with this bar on top, is your estimated mean, and you have sample 1, 2, 3 up to sample n. Sum them, divide by n, you have your mean. Okay. Another way to write this is to use the symbol of the sum, and I don't want in this class to sort of dwell too much into the math and the equations. I'll try to minimize the amount of math and equations you'll have to recognize or be able to understand. This is probably one of the most basic ones, and so making sure you can understand it is important. And this term, this symbol of the sum is sort of very common. And so the idea is that when you have a symbol like this before your variables, it means you sum your variables. Now, you sum what variable exactly? Well, here you can see in our first example, you sum y. So y is here in front of the sum sign. And you sum across what? Well, across your first sample, your first y, up to your nth y. You can write all this in different ways. You can write, so just beside you have sum across i's up to n, or and the next one over is sum where I equals 1 up to n at the top, or the last one over there, you have the sum across i's. And you see that one is convenient. You have yi, so you sum your y's across your I samples, all your samples. Okay, so this is a notation I like. It's easier. So you sum across i's of all your yi, and you divide by n, and gives you your estimate of the mean. But remember, your estimate of the mean will be different, slightly different at least, from your actual population mean. And so you should always think of the numbers you calculate based on the sample size as an estimate. Okay. I have a little example here. So a data set, you have 5 numbers. So you have 5 different numbers. So n goes up to 5. Okay. These are the values. Okay. So if you calculate the mean here, it's going to be sum of all these numbers divided by 5. So you have a mean of 4. Now, to come back briefly to this moment around the mean, so the first moment around the mean, as I said, is always going to be 0. So that's why the first moment is tightly linked to the mean. And basically, the way you calculate that is you do the difference for each sample between the sample and the mean. So the first sample here is 1. So in the first parenthesis here, you have 1 minus 4. Then you do the sum across all your samples. 3 minus 4, so your second sample is 3. 3 minus 4, 4 minus 4, 5 minus 4, 7 minus 4. You sum all that, divide by n, by 5, and you will get, automatically you will get 0, because all your samples will average to, well, the mean, 4, and all the means will average to the mean, 4. And so by definition, it's always going to be 0. So it sounds a little bit trivial, but you'll see in the next equation that you have a progression. And so here, remember and be able to understand and recognize your average for the mean. The next one, the second moment, is the variance. So how variable your number is, or your sample is. And if you look at the equation here, you now might recognize a similar pattern here where you have the difference between your sample and the mean. So this difference here, we had it in the first moment, and we have it here again. So it's the sum across your samples of the difference between that sample and the mean. Little difference here, you square this. Here you divide by n minus 1. Now, we'll see in a second that we'll follow a sort of similar pattern of always having the difference between your sample and the mean, and then you're going to put it to the exponent 2 for the second moment, to the exponent 3 for the third moment, to the exponent 4 for the fourth moment. And this also gets a little bit more complicated. Here, I don't need you to sort of get too much into the details. Here we compensate for the fact that uh, your standard error is always one sample away from your mean. Anyway, um, again here I want you to be able to recognize this. And there's another concept that I think is really important, is that your difference here is squared, right? So this number here in parentheses, this difference is always, this difference squared is always going to be positive, right? Because if you have a difference that's negative, right? If you go back to our example of the mean here, 1 minus 4, it's going to be minus 3. Minus 3 times minus 3 is a positive number. So this makes it such that your numbers are always positive. So it's a distance, if you want, a distance from between your samples and the mean. So that's sort of important, because as you when you calculated the mean, it averaged to 0 because you have numbers that were sometimes below the mean, sometimes above, and if you sum them all, you have negative and positive numbers that average to 0. Here, it's always positive numbers, so it's distance, if you want, so it averages to something that's different from 0, that's above 0, okay? And so s squared, which is your variance, is equal to this, basically this average difference, or this average distance, if you want, between the mean and your samples. The variance is very related to the standard deviation. So often you write the standard deviation as S, or this is a delta. The variance might be delta square. And it's S and S square because the standard deviation is the square root of the variance. So basically it's a very similar number. And they're just off by a squaring factor. Okay. A little example here, same example as before. And you see here my moment around the mean. So 1 minus 4 squared, so a positive number. Specifically here it's 9. 3 minus 4 square is 1. So I add all these numbers, okay, divide by the sample size minus 1, and you get a variance of 5. Okay, so these few numbers here, I just these two calculations here, the variance and the mean, I want you to be able to recognize the equations. And so actually we have a concept map here. Understand what a histogram is, recognizing the equation for the mean, and understand in terms of the standard deviation and the variance how this relates to the same progression, but in this case we take a distance of a value that's always positive. So this distance comes from the squaring. Okay. Stay tuned next for a little bit more on descriptions and distributions.